All right, this is video number 3. We're going to pick up on question M to define the term half-life. This is the time required for the concentration of a particular reactant to reach half of its original value. Now we're going to kind of do some exercises to get a handle on what that means. If we write the integrated rate law for a first order reaction, we see that the logarithm of A at any particular time t is equal to negative kT plus the logarithm of the initial concentration A. Now, if we substitute, for example, the initial value is 100 and the concentration at time t is 50, that would be getting down to half of the original concentration. So we want to try to find what is the time that it takes to do that. So if we simplify and we solve this equation for t, we end up getting the natural logarithm of 1/2 is equal to negative kT. So the half time, or the half-life, is equal to the natural logarithm of 1/2, which would be 0.693 divided by k. So notice the half-life for a first-order rate law does not depend on the initial concentration. The half-life remains constant through the reaction. So going back to our original problem here, how much time was required for the reactant concentration to change from 10 molar to 5 molar? The answer is 30 seconds. How much time was required for the reactant concentration to change from 5 molar down to 2.5 molar? Another 30 seconds. So if the decomp reaction data shows that the half-life is constant over time, then it must be first order. The half-life for a second order reaction is not constant over time, and to verify this, let's go back to our second order data table in part H. If we look at that, how much time is required for the reactant concentration to change from 10 to 5? 20 seconds, but to go from 5 down to 2.5, it's 40 seconds. So that time to cut in half is not the same. Therefore, it is not first order, which we knew going in. All right, let's talk about temperature and rate. Most chemical reactions will occur at a faster rate when the temperature of the reaction is increased. If the temperature is increased, the value of the rate constant should increase. And let's see if we can understand why that is using the collision model. So you should be writing this down in your notes. The rate is proportional to the concentration of A. So if A increases, then the rate increases. Molecules have to collide with each other to react, and the more collisions, the higher the rate. So the higher the concentration, the more collisions you have, and so the rate goes up. Now, let's talk about this same collision model to explain why increasing the temperature causes the reaction rate to increase. Again, we start with rate is equal to K times A. If we raise temperature, the molecules are moving faster, so we have more collisions every second. So the rate is higher. Now, consider the reaction between hydrogen and iodine to form HI. Is it true that every time a hydrogen molecule collides with an iodine molecule, we get a molecule of HI? And the answer is no. And in fact, perhaps surprisingly, only 1 in 10 to the 13th collisions causes a reaction. In most reactions, the reactant molecules have to be oriented in a particular and very specific way relative to each other in order for this reaction to occur. In 1888, Arrhenius suggested that molecules must possess a certain minimum amount of energy in order to react, and this is known as the activation energy. We abbreviate that in chemistry as EA. And the top of a hill in an energy diagram represents an activated complex or some sort of transition state. And this represents the position in the sequence where the bonds are partially broken and partially formed. So if we look at this particular diagram, we are changing CH3NC to CH3CN, and we need to label this diagram. What is going on with this diagram? All right, so we can clearly see the potential energy of the starting material, the reactants, is right here on the left. It's the potential energy of CH3NC. And then over on the right is going to be the potential energy of the products, CH3CN. Then we have to take a look at what the rest of the picture is telling us. Well, up at the top is this activated complex. We have to cross this hill in order for this reaction to occur. And the difference between the top of the hill and the reactant's potential energy, this is called the activation energy. That's the hill we have to get over to make this reaction occur. Now, the difference between the potential energy of the reactants and the potential energy of the products, that's just the delta E for the reaction. So in our case, the reaction is losing energy, so this is going to be an exothermic reaction. The rate of a reaction depends on the magnitude of EA. Explain. Well, the lower the activation energy, the faster the reaction can occur, and that's because less energy has to be supplied to the reactant molecules to be at a high enough energy to react into products. So the reaction goes faster and vice versa. And in terms of this activation energy, explain why the reaction rate tends to increase at higher temperatures. Well, the kinetic energy of all the reactant molecules has a wide range of values. At a higher temperature, the average kinetic energy increases, and so a greater fraction have enough kinetic energy to overcome this hill, this activation energy hill, and that leads to a faster rate. So here we're looking at three different processes, three different reactions, and we need to decide which one of these is endothermic. Well, that would be reaction 3, because the products are at a higher energy than the reactants. Which reaction should occur at the slowest rate and at the fastest rate? Well, the slowest rate is going to be reaction 2 because it has a higher energy barrier to climb between the reactant state and the intermediate, whereas the fastest rate will be 1 because it has a lower hill, a lower delta between the reactants and the top of the hill. All right, now in part M, we want to calculate the activation energy for the reverse reactions for 1, 2, and 3. Number 1 is going to be 25 kilojoules per mole, and you can see where that comes from. That's going to be the difference between the products and the top of the hill. And if we do that same calculation for reactions 2 and 3, we're going to get 40 and 15 for our activation energy for the reverse reactions. But it's pretty easy to see how to calculate it. All right, at the beginning of this chapter, the term reaction mechanism was defined as a step-by-step molecular level view of the pathway to get from the reactants to the products. Every event in the mechanism is called an elementary reaction or an elementary step. And if there is only one molecule as the reactant in an elementary step, that's called unimolecular. If it requires 2 molecules, then it's bimolecular. And if it requires 3 molecules, which is fairly rare, that would be termolecular. So let's look at this first example where we've got NO2 plus NO2 reacting to form NO3 plus NO. Step 2, NO3 plus CO goes to form NO2 plus CO2. What's my overall reaction? Well, in this case, this is sort of like a Hess's law problem in that we're going to add these two reactions together. We're going to see that this gives us NO2 plus CO reacts to form NO plus CO2. Pretty straightforward. Okay. Now, the species NO3 is neither a reactant nor product in this reaction. It's formed in step 1 and it's consumed in step 2. And this is an example of an intermediate. An intermediate is not the same as a transition state because intermediates can be stable and sometimes they can even be isolated, whereas transition states are always unstable and can't ever be isolated. If an intermediate can be detected, it can help to support why a particular reaction mechanism is likely to occur. So now we have to look at this diagram and figure out what the intermediates are and kind of label this diagram. So I'm not even going to try to name these compounds, but you can see what's happening in step 1 and step 2. All right, so here we have a transition state as we get over the hump, get over our activation energy, and yet we have another transition state to get to prior to getting to the reaction products. So in the middle at point B, this is going to be our intermediate. This would be the MoCO5 that you see in step 1 and step 2. All right, in the proposed two-step reaction mechanism, MoCO5 is classified as an intermediate, and CO, carbon monoxide, is classified as a product because it's produced in step 1 and not consumed in any subsequent step. All right, in section 14.3, it was mentioned that a rate law must be determined from experimental data. You can't just look at the coefficients to figure it out, but you can look at the rate laws and the elementary steps of the rate laws, and if the experimentally determined rate law is consistent with the rate law from a reaction mechanism, it supports the fact that that mechanism is valid. The rate law of an elementary step is based directly on its molecularity. And that means that the rate of a unimolecular step is going to be first order, and the rate of a bimolecular step is going to be second order. Now, a reaction mechanism often involves several steps. Each elementary step has its own rate constant, has its own activation energy, and it's often true that one step is much slower than the others. And the overall reaction rate really can't be any faster than the slowest step. It's like when your family tries to get out of the house to go somewhere. The overall speed of your family is dependent on the slowest person in your family. And because the slow step limits the overall reaction rate, this step is called the rate limiting step. This step governs the rate law for the overall reaction. All right, so if we look at this overall reaction again, we know which one is the slow step and which one is the fast step, and we can write a balanced equation. All right, this would just be the sum of the two reactions, okay? When we do that, we get this one, and we can see that the rate law, we can write the rate law proportional to the slowest step, and that's got 2 molecules of NO2, so I would have K NO2 squared. We can't really ever prove a rate law, and all we can say is that the formulation of the rate law is consistent with the experimental data. All right, now we've got another case here where we've got N2O going to N2 plus O in the slow step, and then another step, which is the fast step. And based on this mechanism, we want to write the balanced equation for the overall reaction and then write the rate law for this. So here, when we add up step 1 and step 2, this is our overall reaction, and our rate is going to be equal to N2O squared. And even though there are 2 moles of N2O overall, the slow step is what drives the rate law, and this step is unimolecular. So in fact, I have mislabeled this. This should just be equal to K times N2O raised to the first power. We're going to stop there and have a short video to finish.